Welcome to Tungal Online Classes. In previous video, we have discussed the concept of free body diagram and we have solved some problems on the basis of a free body diagram. Okay, so today we are going to discuss the apparent weight of the person in a lift. Right? The apparent weight of a person in a lift, it is very important for 5 marks. It is very important for 5 marks. Okay, see here, the first consideration part, consider a person of mass EM standing on a weighing machine placed inside the lift. Okay, see here. So consider a person of mass M is standing on a weighing machine and it is placed inside the lift. So this is our consideration part here. So consider a person of mass M is standing on a weighing machine. It is placed inside the lift. See here. So in this case, this person exerting force in downward direction. So that is the weight of the person is acting on the surface of the weighing machine. So that is W. So this is the actual weight of the person, that is W is equal to mass into acceleration due to gravity. So at the same time, the surface of the weighing machine is also exerting some amount of force in opposite direction. So this is known as a normal reaction. So here, the normal reaction that gives the apparent weight of the person. The normal reaction that gives the apparent weight of the person. So here R is equal to, that is apparent weight of the person. Apparent weight of the person. Okay, see here R indicates that apparent weight of the person and W indicates that is the actual weight of the person. Okay, see here we will discuss the variation of apparent weight of a person when the lift is at rest, when the lift is moving for motion in upward direction or downward direction. Okay, see here the first case, when lift is at rest, when lift is at rest, when lift is at rest. Okay, see here. First we are going to draw free body diagram for the system. So consider this is a point object. So in this case, the weight of the person is acting in the downward direction and the normal reaction is acting in the upward direction. So in first case, when lift is at rest, when lift is at rest means in that case, the acceleration of that lift is 0. The acceleration of that system is 0. Next, then we are going to determine what is the net force acting on this system. So here the net force is nothing but net force that is equal to normal reaction R minus weight. Normal reaction R minus weight. So here the net force is nothing but it is the product of mass into acceleration that is equal to R minus W. So here the lift is at rest. The lift is at rest means the acceleration of the lift is 0. If the acceleration of the lift is 0, so the 0 into unit term is 0. You see here mass into 0 that is equal to R minus W. That is equal to R minus W. Here 0 into unit term is 0. So then this is 0 is equal to R minus weight or R is equal to weight. So here what do you mean by R? So R is nothing but that is the apparent weight of the person and W indicates that that is the actual weight of the person. So here if the lift is at rest means the apparent weight of the person that is equal to the weight of the person. Apparent weight of the person that is equal to weight of the person. Okay, see AP indicates that apparent weight of the person that is equal to actual weight of the person. That is the actual weight of the person. Okay. The next one, second case. When lift moving uniformly in upward direction or in downward direction. So the second case here, when a lift is moving uniformly in upward direction or downward direction. case here we will draw a framework diagram here. So in this case, this is the weight of the person, and this is the normal reaction. Okay, see here, when lift is moving uniformly in upward or downward direction. So uniformly means, the uniform motion means it covers equal distance in equal intervals of time, or equal displacement in equal intervals of time. In that case, the acceleration of the system is also zero. If the system is moving in uniform motion, in that case the acceleration is zero. If the acceleration is zero means again the apparent weight of the person, that is equal to the actual weight of the person. Okay, see here, your condition is uniformly or uniform motion, so then acceleration of the system is zero. So then net force acting on the system, that is equal to r minus w. The net force is nothing but mass into acceleration, that is equal to r minus w. So next here acceleration is zero, zero into w is zero. So then this equation becomes r is equal to w. R is equal to w. Here r indicates that apparent weight of the person, and w indicates that the actual weight of the person. So next, third case. When lift moving upward direction, when the lift moving upward direction with an acceleration d. So what is the third case here? When lift is moving upward direction with an acceleration d. Okay, here first we have to draw three-point diagram here. So that is the weight of the person is acting in the normal direction, and this is the normal reaction, that is r. Here the direction of acceleration is in upward direction. So then the net force acting on this system, that is equal to, so here the acceleration of the system is in upward direction. So in this case the normal reaction is more comparing to the weight of the person. So the net force acting on the system is, that is r minus weight. The net force is equal to r minus weight. Here net force is nothing but product of mass into acceleration. Here mass is m and acceleration is a, that is equal to r is apparent weight as it is a normal reaction minus weight. So weight is nothing but the product of mass into acceleration due to gravity, that is m into g. That is, so the net force is nothing but the product of mass into acceleration, that is equal to normal reaction minus weight is nothing but the product of mass into acceleration due to gravity. So then in next step, take this minus mg to this side, then it becomes r is equal to m a plus mg. So in this case take m common, then r is equal to m bracket of a plus g, m bracket of a plus g. So this indicates that the apparent weight of the person, that is equal to m bracket of a plus g, right? See here, apparent weight of the person increases when the lift is moving in upward direction. The apparent weight of the person increases when the lift is moving in upward direction. So in this case, the apparent weight is greater than weight of the person, or actual weight of the person. Right? Here R indicates that apparent weight of the person, and here W indicates that the actual weight of the person. When the lift is moving in upward direction, the apparent weight of the person is greater than the actual weight of the person. Or if the lift is moving in upward direction, the weight of the person is, apparent weight of the person is increases. The apparent weight of the person is increases. Right? In the next case, case number 4, when the lift is moving with an acceleration a, in downward direction, in downward direction. Okay, see. So first, what is the condition here? The lift is moving with an acceleration a in downward direction. First, draw the free body diagram here. So this is the system, the weight of the person or weight of the system acting in the downward direction, and the normal reaction R is acting in the upward direction. So here the direction of acceleration is in downward direction. The direction of acceleration is in downward direction. Okay, see it. So then the net force acting on this system, the net force acting on this system, that is equal to, so in this case the weight of the system is more compared to the normal reaction. So the net force is equal to weight minus normal reaction. Weight minus normal reaction. Here net force is nothing but mass into acceleration, and weight is nothing but mass into acceleration minus, that is R. Okay, take this on the side, so that it becomes R is equal to mg minus me. This is equal to, take m common, this is g minus b. This is g minus b. So this is the apparent weight of the person when the left is moving in downward direction. So apparent weight of the person when the left is moving in downward direction with an acceleration is d. So that is R is equal to m bracket of g minus e. G minus e. So in this case, the apparent weight of the person decreases when the lift is moving in the downward direction. So here, the weight of the person, it is greater than the apparent weight of the person, right? So in a fourth case, when the lift is moving with an acceleration in downward direction, in that case, the apparent weight of the person is decreases when the lift is moving in the downward direction. When the lift is moving in the downward direction. And the last case number 5. Last case, the lift falls freely, right? And the lift falls freely. And the lift falls freely. Okay, see it. So lift falls freely means in that case, that lift is moving in the downward direction. So this is the condition here. That is R is equal to m bracket of g minus c. R is equal to m bracket of g minus c. So when the lift is moving in the downward direction, the apparent weight of the person, that is equal to m bracket of g minus c. M bracket of g minus c. Okay, see it. If the lift is falls freely means in that case, the acceleration of that lift becomes acceleration due to gravity. So in that case, the acceleration of the lift that becomes acceleration due to gravity. Then substitute the value here. Then normal reaction or apparent weight of the person, that is equal to m bracket of g minus c. Here g minus g means that is 0, right? 0 in chemical means 0. Then the apparent weight of the person is 0. The apparent weight of the person is 0. So this is about the apparent weight of a person in an lift. So here first we are considering a person is standing on a weighing machine. It is placed inside the lift, right? So here the person exerting some amount of force on the weighing machine. So that is nothing but the weight of that person acting in downward direction. At the same time, the weighing machine also exerting the same amount of force on the person in opposite direction. So that gives the apparent weight of the person. So there are 5 cases. The first case is when lift is at rest. When the lift is at rest means in that case the acceleration of that system is 0. If the acceleration is 0 means the net force acting on that system is apparent weight or the normal reaction R minus weight. R minus weight. So net force is 0. Then R is equal to weight. In that case, the apparent weight of the person, that is equal to actual weight of the person. The apparent weight of the person, that is equal to actual weight of the person. So next case, when the lift is moving uniformly in upward direction or downward direction, here the condition is uniform motion. If the body or if the system is moving in a uniform motion, then the acceleration of that system is 0. If the acceleration is 0 means the net force acting on the system is 0. So then net force equal to R minus W. Net force is 0 means R is equal to W. So if the net force is 0, then R is equal to W. R is nothing but the apparent weight of the person, and W indicates the actual weight of the person. So here is also the apparent weight of the person, that is equal to actual weight of the person. And the case number 3, when the lift is moving upward with an acceleration in c. So in this case, that lift is moving with an acceleration So here the upward weight of the person is more comparing to the weight, or the normal reaction is more comparing to the weight. So the net force acting on the system, that is equal to R minus W. So here the net force nothing but is the product of mass into acceleration, m that is equal to R minus m into g. So then simplify this one, we will get R is equal to m bracket of a plus g. So in this case, the apparent weight of the person increases when the lift is moving in upward direction. And the next case, when the lift is moving with an acceleration a in downward direction. So here, the lift is moving in the downward direction with an acceleration is a. So then, the net force acting on the system, that is equal to weight minus normal reaction. So here weight is more comparing to the normal reaction. The net force is nothing but is the product of mass into acceleration, that is equal to weight is m into g minus r. Simplify this one, we will get r is equal to m bracket of g minus a. R is equal to m bracket of g minus a. In this case, the apparent weight of the person decreases when the lift is moving in a downward direction. And the last case, when the lift falls freely, means in that case, the acceleration of that system, that is equal to acceleration due to gravity. So substitute the value in this equation, then apparent weight of the person is 0. The apparent weight of the person is 0. To note point, tension in the cable. Okay, so here consider this is a lift. A person is standing inside the lift, right? And this is a cable. So in this case, we are going to determine what is the tension developed inside the cable, right? When the lift is moving in upward direction and when the lift is moving in the downward direction. Okay, see, the first case, if the lift is moving in upward direction with an acceleration d, right? Okay, see, so this is a cable. We are going to find out what is the tension developed inside the cable. So here, the direction of the tension inside the cable is the point of contact is always away from the point of contact, and the weight of this system, it is acting in the downward direction. First we have to draw free body diagram of this system. So consider this a point object, and here the weight of the system, it is acting in downward direction, and the tension is acting in the upward direction, and the whole system, it is moving in upward direction with an acceleration is a. Okay, see here. So then net force acting on the system, so that is tension minus weight. From this one we want the tension, right? So tension is equal to net force plus weight, right? Okay, tension is equal to net force is nothing but mass into acceleration plus weight is nothing but mass into acceleration due to gravity, and tension is equal to take m common a plus g, right? Okay. See here, the tension developed in the cable and the lift is moving in upward direction. So that is m bracket of a plus g. So here m is nothing but the mass of the lift plus mass of the person. So here m indicates that is the mass of the lift plus mass of the person. So then the tension developed in the cable, that is equal to m bracket of a plus g. So next case, second one. If the lift is moving in downward direction, so in second condition, the lift is moving in the downward direction with an acceleration is a. The lift is moving in downward direction with an acceleration is a. So here this is the weight and this is the tension developed in the string. Okay, see here, the net force acting on the system, that is equal to, in this case, the weight of the person is more comparing to the t value. Then it is net force equal to weight minus tension. So tension is equal to weight minus net force. Here weight is nothing but mass into acceleration due to gravity minus net force is mass into acceleration. So then T is equal to m bracket of g minus e. So this is the tension in the cable when the lift is moving in the downward direction with an acceleration is a. Okay, see here is also same. M is nothing but that is the mass of the lift plus mass of the person or mass of the passenger inside the lift. So in this problem, so this NCERT 5.13 problem. A man of mass 70 kg stands on a weighing scale in a lift which is moving. The first one upwards with a uniform speed 10 meter per second, downwards with a uniform acceleration of 5 meter per second square, and the next one upward with a uniform acceleration 5 meter per second square. What would be the reading on the scale in each case? Next, what would be the reading if the lift mechanism failed and rendered down freely under the gravity? Okay, see it. So first one, write to the given term. The mass of the person is given, that is mass is equal to 70 kg. Mass is equal to 70 kg. And take here g is equal to acceleration due to gravity is equal to 10 meter per second square. 10 meter per second square. Right? Okay. What is the first one here? The upwards with a uniform speed. Upwards with a uniform speed means, so in this case the acceleration of the system is 0. If the acceleration is 0, in first case, if the acceleration is 0, so then apparent weight, that is R is equal to W. R is equal to W. Then W is nothing but mass into acceleration due to gravity. Here the mass of the person is, that is 70 into acceleration due to gravity is 10. This is equal to 700 Newton or kg weight. 700 kg weight. Okay. The second case. What is the second case here? Downwards with a uniform acceleration of 5 meter per second. So in this case, the lift is moving in the downward direction with the acceleration 5 meter per second square. Right? Okay, see here. R is equal to this condition. The upright weight is equal to m bracket of g minus a. M bracket of g minus a. And upright weight that R is equal to m. Mass is 70 and acceleration due to gravity value is 10 minus acceleration is 5. So 10 minus 5 is 5. 5 into 70 is, that is R is equal to 350 kg weight or Newton. R is equal to 350 kg weight or Newton. Third case. In third case, when the lift is moving with an acceleration a is equal to 5 meter per second square in upward direction. Then apparent weight of a person, that is equal to m bracket of a plus g. M bracket of a plus g. So this is equal to mass is 70 and acceleration is 5 plus acceleration due to gravity is 10. 5 plus 10 is equal to 15. 15 into 70. So 70 into 50. 70 into 15 is 1050 Newton. This is the apparent weight of a person when the lift is moving in upward direction with an acceleration is 5 meter per second square. And the last case, if the lift falls under freely, that means the acceleration due to gravity or acceleration both are equal. So here a is equal to g. So then R is equal to m bracket of g minus a. Here a value is g. So g minus g is equal to 0. In that case, the apparent weight of the person in the lift is 0. The apparent weight of the person in the lift is 0. Okay, see here, in first case, the lift is moving upwards with a uniform speed of 10 meter per second. Here they are mentioned uniform speed. So then the acceleration of the system is 0. If the acceleration of the system is 0 means the apparent weight of the person, that is equal to actual weight of the person. So that is 700 kg weight. In second case, the lift is moving in downward direction with an acceleration of 5 meter per second square. So then here acceleration is 5 meter per second square. If the lift is moving in downward direction means in that case the apparent weight of the formula, so that is equal to m bracket of g minus a. So substitute the values here, we will get the answer is 350 kg weight. And the next case, if the lift is moving with an acceleration 5 meter per second square in upward direction. So this is a formula to calculate the apparent weight of a person when the lift is moving in the upward direction. So in that case, R is equal to 1050 Newton. So last one, if the lift falls freely under gravity, so in that case acceleration is equal to acceleration due to gravity, then the apparent weight of the person is 0. Okay, see here, when the lift is moving in the downward direction, the apparent weight of the person is 350 kg weight. So here the weight of the person is decreases. Actually, the actual weight of the person is 700 kg weight, but when the lift is moving in the downward direction, the apparent weight of that person is 350 kg weight. In that case, its weight is decreases. When the lift is moving in the downward direction, the apparent weight of the person is decreases. Similarly, when the lift is moving in the upward direction, its weight becomes 1050 Newton or kg weight. So in that case, the apparent weight of the person is increases when the lift is moving in the upward direction. If the lift falls freely, in that case the apparent weight of the person is 0. The next concept is impulse. So impulse means it is a product of force and time. So it is denoted by J vector. Okay, see here, that is J vector, that is equal to, it is a product of force and time, right? Okay, so here what is the SI unit of impulse here? The SI unit of impulse, is Newton second, and the next one, CGS unit of impulse is, that is dyne second, and the next one, dimension formula of impulse, so that is m l t to the power is -1, and the next one, it is a vector quantity, So in this case, the impulse is a vector quantity, means it's having both magnitude and direction. Then the direction of an impulse, it is similar to the direction of a force. Okay, so next one, we are going to consider a body of mass is m, and it is initially moving with a velocity, that is u, and after some time interval t second, its velocity changes to v. Okay, here we are going to find out the impulse. So that is impulse is equal to force into time. So force is nothing but it is a product of mass into acceleration into time. So here m indicates that mass, a indicates that acceleration, and t indicates that time. So already we know that the equations of motion, that is v is equal to u plus at. So from this relation, a is equal to v minus u divided by t. Okay, substitute here, that is mass, a value is, that is v minus u divided by t into time interval is t. So in this case, t get cancelled, the remaining is m bracket of v minus u. So then impulse is equal to, it is a product of mass into velocity minus mass into velocity. Here m indicates that mass, v indicates that final velocity, minus mass into initial velocity. So this is nothing but the final momentum. This is nothing but final momentum minus this is nothing but initial momentum. So then impulse is equal to final momentum minus initial momentum is, that is change in momentum. So it is very important for 3 marks. Okay, so this is about the impulse here. So first of all, what do you mean by the impulse? Impulse means it is a product of force and time. The SI unit of impulse is Newton second, and the CGS unit of impulse is dyne second, and the dimension formula is mlt to the power is -1, and it is a vector quantity. It is a vector quantity means it is having both magnitude and the direction. The direction of an impulse, it is similar to the direction of a force. So after that, we are considering a body of mass m. Initially it is moving with a velocity, that is u. So after some time intervals, its velocity changes to v. So then we are going to find out the impulse here. Then J is equal to force into time. So if force is nothing but it is the product of mass into acceleration into time. here acceleration is nothing but that v minus u divided by t. So the acceleration in terms of final velocity, initial velocity and the time interval, here tt get cancelled. So then multiply this one, mv minus mu. mv is nothing but the product of mass into velocity is nothing but the momentum. So here this is the final momentum minus initial momentum. So then the impulse is equal to change in momentum. Impulse is equal to change in momentum. Okay, see here the impulse that is equal to f into t, that is equal to change in momentum. Change in momentum. So this is about the impulse. Graphical method to calculate the impulse. The first one is by constant force and the second one is by variable force. The first one by constant force means, so here the force at any time interval is same. So that is known as the constant force. Okay, see here. So in this case we are going to draw a graph versus force versus time. The force is taken along the y-axis and the time is taken along the x-axis. Okay, see here. So the time interval we are considering this is 0, 1 second, 2 second, 3 second, 4 second and so on, 5 second. And here the force is that is 1 Newton, 2 Newton and 3 Newton, so on. So in this case we are considering, so this board is a one object, we are applying the 1 Newton force on this board, right? Okay, see here. So at the time interval of 1 second the force is 1 Newton, at the time interval of 2 seconds the force is 1 Newton, at the time interval of 3 seconds the force is 1 Newton. So in this case the force it is same with respect to the time. With respect to the time, so this is known as the constant force. Okay, join all these points here. Next we are going to find out what is the area under this graph. So in this case consider this is O point and this is A point, this is a B point and this one is the C point. So here we are going to find out the area under this diagram, the area under this graph. Okay, so area under force and time graph, force and time graph. So this is equal to, so it is look like a rectangle here, the area of a rectangle, that is OABC, right? Okay, this is equal to, so in this case the formula to calculate the area of a rectangle is that is length into breadth, that is OA into AB, OA into AB or BC into OC. Here OA value is nothing but that is a force, that is F, and AB value is nothing but the time interval. Let us assume that this is a T1 and this is T2. At this point is T2. So then T2 minus T1 is nothing but that is del of T, change in time interval, right? So this gives the impulse, force into change in time interval or the force into time, that is known as the impulse. Okay, see here. The area under the force and time graph that gives the impulse. So here the important point is area under force time graph gives impulse. Okay, and the next one by variable force. Next one is by variable force. So variable force means the magnitude of the force that changes with respect to the time. The magnitude of the force that changes with respect to the time. Okay, see here. So in this case, this graph represents. So this is a force and this is a time. So this graph represents a variable force acting on the body. Okay, see here. So consider this is the initial point, that is a T1, and this is a final point, that is T2. The time interval at this position is T1 and that position is T2. So in this case that force it changes, the magnitude of the force that changes with respect to the time. At this time the force is this much, at this time the force is this much. So here this graph indicates that the variable force is acting on the body. Variable force is acting on the body. So here we are going to calculate the impulse. To calculate the impulse, so in that case we are assuming that the force must be a constant. The force must be a constant. But in this case the force is variable. Then how to find the impulse in this case? Okay, see here. So in this case the force acting on the body is variable force. For that one we are dividing this entire graph into small intervals or a small segment. We are dividing this entire graph into small segment, right? So here we are dividing this entire graph into small segment in a such a way that the force between these 2 points is approximately constant. The force between these 2 points is approximately constant. If the force is approximately constant means the area under this segment, that gives the impulse. For example, that value is del of J1 or that impulse value is J1, right? Okay. See here, again we are dividing this graph into smaller segment. The area of this one that gives the impulse. So this is J1 and this is J2. Similarly, entire graph we are dividing into smaller segment, right? Okay. So here the area of this all smaller segment that gives the impulse. So this is J1, J2, J3, J4, so on up to J suffix n, right? So then the total impulse, so that means it is J1 plus J2 plus J3, so on J suffix n. So in simple way we will write this one: impulse that is equal to integration of force into change in time interval, that is del of t or dt, right? Okay, see here, impulse that is J vector is equal to integration of force into del of t. Here integration from the initial point is t1 to t2, so t1 to t2. So then what is the meaning of here integration? So integration means it will add all the impulse. So for example here the impulse is J1, J2, J3, J4, J5, J7, so on J suffix n. So according to this expression it will add from the time interval t1 second to the time interval of t2 seconds. So that is a J vector is equal to integration of t1 to t2 f into dt, right? Okay. So here the graphical method to calculate the impulse, there are two methods. One is by constant force and one more is by variable force. By constant force, so here the area under the force time graph that gives the impulse, area under the force time graph that gives the impulse. Then by variable force, in this case we are dividing the entire graph into very smaller segment. We are dividing that entire graph into smaller segment in a such a way that the force acting between these 2 points is approximately constant. After that we are going to find out the area of this segment that gives the impulse, right? Okay, so this is J1, so on up to Jn, right? Jn. So next one, the general formula to calculate the impulse by variable force is J is equal to integration of t1 to t2 force into dt,